In the previous videos, we have studied the effect of Lorentz transformations on the coordinates. Now we are going to study the effect of the Lorentz transformations on the velocity of a particle. And we are going to consider just the simplest or the most genuine Lorentz transformations, which are the Lorentz boosts. Genuine in the sense that the rest of the Lorentz transformations are rotations or compositions of boosts with rotations. So we just take Lorentz boosts, and we are also going to study them in the simplest setup. This setup is the same that we considered in the previous case to find the form of the Lorentz boosts. In this setup, the two inertial reference frames that we're considering, 1 and 1 prime, have parallel axes and coincide, their origins coincide at time equal 0. So after some time, as it is drawn here, the origins start separating at the velocity v, but only along the direction x1. So the indices, the axes x1 and x1 prime, which are parallel, still coincide, although their origins are separated, and the rest of the axes, I am only representing the axis x2 and x2 prime, remain parallel, but they are separated. Here I have drawn a particle, a point particle, and the speed of this particle, the velocity, has components ui and ui prime in the prime or second reference frame. How is ui defined and ui prime? So ui is, of course, the derivative of the position of the particle with respect to the time measured in that reference frame, in the reference frame 1, in the unprimed one. It is convenient to divide this velocity by c, because then we have the derivative of xi with respect to x0. In the prime reference frame, we just add primes everywhere. Now we can just express xi or xi prime and x0 or x0 prime in terms of the coordinates of the other reference frame using Lorentz transformations. In this case, for the sake of convenience, we are going to express the unprimed coordinates in terms of the prime ones. In the previous video, we had obtained the transformations to go from the unprimed to the primed coordinates. Okay, let me remind you what this expression was. In the simplest form that we obtained, so this was hyperbolic cosine of some parameter phi, which is given by the velocity, and I will write later, plus the hyperbolic sine of the same parameter times x1, and x1 prime was given by the hyperbolic sine of this parameter phi times x0 plus the hyperbolic cosine of that parameter times x1. The hyperbolic cosine was given by 1 over the square root of 1 minus v divided by c squared, while the hyperbolic sine of phi was minus v divided by c divided by 1 minus v divided by c squared. Okay, so now we want x0 and x1 as functions of x0 prime and x1 prime. In other words, we need the inverse Lorentz transformation, the one that takes us from the quantities measured in the primed reference frame to the unprimed one, from 2 to 1. Now this is very simple, but there are several ways of arriving to the same form. First of all, you can observe that from the point of view of the second frame, the frame number 1, the unprimed one, moves with velocity minus v instead of v. So you just have to do this transformation everywhere. Replace v by minus v. Now if you look here in the expression of hyperbolic sine, you see that this takes the hyperbolic sine to minus the hyperbolic sine of phi, but the hyperbolic cosine remains the same. It's even under this transformation. Okay, this corresponds to phi going to minus phi, because the hyperbolic sine is odd and the hyperbolic cosine is even. So we just have to do this replacement in the transformation, the hyperbolic sine by minus the hyperbolic sine and the hyperbolic cosine by the same. Just don't replace it. In other words, if lambda of phi is this Lorentz transformation, then the inverse of maybe you prefer to write it in this way if we want to be very precise. So the inverse is really the same matrix, but with phi replaced by minus phi. So cos phi minus sin phi minus sin phi cos phi. Okay, you just multiply these two matrices and you check that lambda times lambda minus 1 is equal to the identity. So there is an easy way to arrive to the same result. You just have to prove, okay, that if you multiply two of these matrices, the resulting matrix just has the same form. It is a transformation of the same form, which you expect because it should be a Lorentz transformation, another Lorentz boost. But the parameter is just the sum of these two parameters. This automatically tells you that, okay, well, this plus the fact that if phi is 0, this is the identity because the hyperbolic sine of 0 is 0 and the hyperbolic cosine is 1. Okay, so these observations immediately lead you to this result that we are after, which is that okay, this is maybe I'll do it here. The transformation we want is x0 is equal to cos phi x0 prime minus hyperbolic sine of phi x1 prime, and x1 is minus the hyperbolic sine of phi x0 prime plus the hyperbolic cosine of phi x1 prime. Okay, now we go back to the definition of velocity, and we just take the component 1 in the frame 1 or the unprimed 1, and we need dx1 and dx0. We can compute this here immediately, just taking the derivatives and taking into account that the cosine and of phi is constant, and also the hyperbolic sine is constant, and so on. Okay, so I get here minus the hyperbolic sine of phi dx0 prime plus the hyperbolic cosine of phi dx1 prime divided by hyperbolic cosine of phi dx0 minus the hyperbolic sine of phi dx1 prime, so it's prime here. Now we divide everything by, numerator and denominator by dx0 prime, and we get minus hyperbolic sine of phi plus hyperbolic cosine of phi, and dx1 prime divided by dx0 prime, okay, just apply this definition but with primes, is u1 prime divided by c, and in the denominator we get hyperbolic cosine of phi minus the hyperbolic sine of phi, again times u1 prime divided by c. Now if we want, we can replace the values of the hyperbolic sines and cosines. This is just v divided by c. Remember the hyperbolic sine of phi was minus v divided by c, so we have to change the sign, divided by these square roots, but this 1 over square root of 1 minus v divided c squared is a common factor in both the numerator and denominator, so we just remove them everywhere. So here we just get u1 prime divided by c and 1 plus b divided by c and u1 prime divided by c. Okay, we can multiply, if we want, this result by c in both sides, so we would get that u1 is v plus u1 prime divided by u plus v divided by c u1 prime divided by c, and this is the first result we were after. Of course, we have still to find the relation between u2 and u3 with the rest of the velocities. This is commonly called the law of addition of velocities. And okay, it is interesting to see what are the properties or the implications of this law. So this law is called addition of velocities instead of transformation of velocities, which would be probably more appropriate or more precise, because as a matter of fact, this transformation is a sum of velocities. The velocity that one measures in the prime, in the moving reference frame, okay, you have to add to it the velocity of that frame in order to find the total velocity that you measure in your rest frame, if we are in the frame 1. In the Galilean case, so how do you get the Galilean limit or the Newtonian limit or non-relativistic limit? So this is the limit in which the speed of light is very large compared to any other speed, so in particular v divided by c goes to 0, and of course u1 prime divided by c go to 0. In this limit you get this Galilean law, okay, which is really just an addition of velocities. So one property of this formula is that indeed you get the right or the correct Galilean limit, non-relativistic limit. Which is the Galilean transformation law. Another property that this formula has is that it is symmetric in V, the interchange between V and U1 prime. Of course, it doesn't matter if it is the reference frame that moves at the speed U1 and the particle at the velocity V in that frame. You just have to add the velocities, and clearly you get the same U1 in the rest frame. So that is also correct, or what you expect. And okay, you can now analyze what happens if, so this would be the first thing that you check, the second thing that you check. The third thing that you check is what happens if U1 prime divided by C is equal to 1. Okay, this means that U1 prime is C, which is the speed of light. So we are trying to see what happens if I am trying to measure the velocity of light in my reference frame, knowing that somebody in the moving reference frame has seen or measured that the velocity of light is C. So you just apply this formula blindly, and you find that this is 1 plus V divided by C, and U1 prime is divided by C is 1. Okay, and you take a common factor C, and you see that the numerator and denominator are equal, and this is just equal to C. So everybody says that the speed of light is C, independently of the motion of its reference frame, which is what the principle of special relativity tells us. So this law agrees with that reference principle. Finally, okay, and this is an observation that maybe it's a bit too early to be made. Observe that the transformation of the coordinates are linear. Lorentz transformations are linear. However, the transformation of the speeds is not linear. It has this denominator here that also contains U1 prime. So this law is not linear. We are going to say that this transformation law is not tensorial. Okay, this you probably don't know what it means, not tensorial, but it will be important in what follows. This is something to remember. I will at some point remind you that we said that this velocity computed in this way does not transform linearly and does not transform as a tensor, which is a problem in what follows. Now we can also compute the transformation law for the other components. Okay, so U2 or 3 divided by C are the x2 or the x3 divided by the x0, and we know that they do not transform, so they are the x2 or 3 prime divided by, and this x0 does transform. We have the transformation here, so it is hyperbolic cosine of phi, the x0 prime minus hyperbolic cosine of phi, the x1 prime. Then if you divide again numerator and denominator by the x0 prime, what you get is u2 or 3 prime divided by c divided by the hyperbolic cosine of phi minus the hyperbolic sine of phi u1 prime divided by c. You can multiply both terms by c, etc., and find a simplified formula. after replacing the values of cos phi and sin phi by the expression in terms of the velocity, you find that this is u3 prime divided by 1 over the square root, this square root that I'm not going to write explicitly, plus v divided by c u1 prime divided by c, and everything divided by this square root. So we multiply again numerator and denominator by this square root, and you find that this is 1 minus v divided by c squared, and then u2, 3 prime divided by this factor 1 plus v divided by c u1 prime divided by c. So this is in the end the transformation law for the other two components.